And I would like only to say that during the years I realized how useful can be functional analysis for application, optimal control, and similar problems. So it's my pleasure. You have the floor.
Thank you very much. Thank you very much. Thank you for being here, and special thanks to Professor Stoyanova for making this conference. Okay. Let me begin with something which is not good to say, but we had a dilemma. That is, we were lazy last year. Bournemouth was 1 year before. So we have something really essentially new to say. But we know that it's not pedagogical for our doctoral students to speak on the same. So it's not good. And we teach them not to speak about something which is very fresh and not well understood. So this was a dilemma, and here is the solution. Some repetitions are needed as well about importance of functional analysis, of course, but the importance of the notion of subtransversality, let me say that Alexander Joffe already spoke about it, and he is the man who taught us that this is really very important. We use it. The first thing to use is something which is already 5 years old, a Lagrange multiplier rule, where subtransversality plays important role. So, finding a Lagrange multiplier reduces to proof that some sets are subtransversal, provided that the density of some the difference of some norms. The other ingredient is so again more proof about the importance of subtransversality. And the other ingredient is the idea of perturbing and then correcting to recover a set which belongs to Burvenis Troibas as far as 85. And here, okay, now you see that I try to skip the introduction, formulate again theorem which we proved 3 years ago maybe now, and we are trying to understand how to use it. So this is a variational condition. You have two Banach spaces, and the epigraph of a function defined on them, which is lower and continuous, in order to epigraph to be closed, for the epigraph to be closed. So you perturb, I don't know, anyway, you perturb a bit, but on the first variable, and you have to recover the epigraph by some correcting set. Of course, you should put some constraints on the correcting set, or if you use the ball of X, it will be trivial. So here is the abstract setting of the problem to formulate the theorem. Xy are Banach spaces. T is a bounded linear operator as its graph. We minimize the functional subject to some translation of the graph as. And here is the theorem. the epigraph of the functional satisfies the variational condition with a correcting set, which has one measure of non-compactness, not the correcting set, but the first coordinate minus t, the second coordinate, has one measure of non-compactness strictly less than 1, then you find the Lagrange multiplier, which is in the annihilator of the graph of your bounded linear operator, and which is non-negative on the cloud tangent cone to the epigraph of phi. So of course it's abstract. Of course it's abstract, and we formulated it, and we aim to apply it to optimal control, to problems of calculus and variations, to problems of optimal control. So normally in this talk, X will be the space L infinity, values in Rn, with the usual essential supreme norm. Y will be L1 with the usual L1 norm, and T is the integration operator. Clearly it's bounded of norm 1. And the good thing is that it maps weakly compact sets to totally bounded set in R1. So, speaking about correction, we are going to use this thing about correction. We will be satisfied with correction sets which their first coordinate is compact set plus some small ball of radius x, Rx. Second coordinate is weakly compact in L1 with some ball of radius epsilon. And the point is that some of these radius should be strictly less than 1. Then the variational condition, then a variational condition with such a correcting set, the assumption of the theorem would be satisfied. The ball measure of non-compactness of ux minus tuy would be strictly less than 1. So these small balls, okay. These small balls, in fact, they are not needed. I mean that if you can correct with something like this, then in the proof of the theorem you build bigger and bigger correction sets. But still compact, to find some compact which is correcting, but it's hidden in the proof of the theorem and it's not trivial. And for application, it's much easier to check the small ball condition. Okay. So to apply it, we of course think about optimal control problems or calculus of variation problems, and we have say that okay, the real infinite dimensionality is the graph. This is the dynamics. One of the variable is the derivative of the other one. This is the real infinite dimensionality. The other things, you put some constraints. Could be, usually they are finite dimensional for people who want to apply it. Pointwise, I mean. So if you have a closed subset of x times y, then we can consider another functional which is the old one and plus infinity outside the constraint, and So, of course, the minimum of this functional and the minimum of phi under the constraints sigma is the same. And one can try to put in sigma intersection of some constraints of usual type which are commonly used. Mixed constraints, pure states constraints, integral constraints, anything unique. Okay, so before speaking about the applications, let me say that one can try to, if you can correct to satisfy one of the constraints, and then you try to correct to satisfy the second of the constraints, it's not very clear, are you able to satisfy with a reasonable correcting set the intersection? Can you go to the intersection? And here is a very simple case when you can go to the intersection, combining. So here you have one set and in Z1 and correcting set for it, and the other one is already in the Cartesian product, and the correcting set for it, but on the second coordinate, and then you can combine. This is a very simple observation. You can combine, and having totally bounded, weakly bounded, weakly compact, you can do the thing. But we are trying to use this for different choices of Z1 and Z2. So, first let me speak just a bit about mixed constraints and make the simple observation that whenever this is the usual thing about the dynamics, whenever the dynamics is governed of the problem is governed by a differential equation whose right-hand side is Lipschitz with respect to the Hausdorff metric, then you can write the graph of this. This is the second coordinate belongs to f of the first coordinate, and then in fact the set of solutions to the differential equation, to the differential inclusion, is intersection of this linear space, this one. Okay, this is a fine space because it's translated. I'll speak about it as the dynamics of calculus of variational problem. And this set which is defined purely pointwise. So, dynamics governed by a differential inclusion is dynamics of the calculus of variations, subject to a mixed constraint. When the set valued map is integrably Lipschitz, then the variational condition for the epigraph of something which is good intersected with psi. You can go back to the graph intersected with S. You can go back to the graph using the correcting set, which is weakly compact in the second variable. Weakly compact because it has summable measure on this kind, this up. So the simplest possibility for weak compactness. And moreover, so G, you can go back to G using a correction which is with compact. Moreover, the clock tangent cone to the graph, looking at it as a set in x, y, so from an infinite dimensional point of view, in fact, it's finite dimensional, so these are all selections of pointwise clock tangent cone. So a lot of this is the work done is going from finite dimensional to infinite dimensional and back. Now Mira is trying to get rid of to do the same for non-autonomous case. Let's see. Okay. So for pure state constraints, I want to give. Of course, we can always write pure state constraints, but we want them to be such that you can correct by a compact set, so they to be massive. We want them to be massive in order to prove something in this way. So about integral constraints, if you have a strictly differentiable function on x, then the level set is massive, provided you see that the image is finite dimensional. The image is finite dimensional. So strictly differentiable, and okay, it's really easy, but easy if you use the small one. Okay. And of course, the most usual thing is that when you have a closed subset of Rn and you look at these trajectories, or it's the phase space XL infinity, which are almost everywhere almost everywhere belong to phi. So this is H, this is already in L infinity. And an easy sufficient condition for this pure state constraint to be massive in L infinity is the clock tangent cone to phi to have non-empty interior. If you assume non-emptiness of the interior of the clock tangent cones, then you can prove that in fact H is much better. It has a hypertangent in the infinite dimensional Banach space already, which is a really strong conclusion. So you can use a correcting set which consists not just compact, it consists of single. It consists of. Okay. So what we can do using this we can recover big part of the most maybe popular Pontryagin maximum principle for with pure state constraints. So you have Lipschitz, an integrably Lipschitz differential inclusion. H is a closed subset of X, so it's a bit abstract still, but you can use both pointwise or integral constraints, whatever, or terminal. It goes in the other basket. And you consider my problem, that is you minimize some Lipschitz function on the terminal point. So if x were continuous, this is just the value of x at the last moment at b. And for L infinity is not that good, but of course you can extend the Dirac function to something of norm 1 again, to L infinity, and use it. Was the bad assumption, but it is present in Winterfeld anyway. Assume that H is massive at the local solution, of this point. So what happens then? Of course we can try to apply the theorem I spoke about to the epigraph of the functional, where phi you have intersected the epigraph of the original functional with putting plus infinity on the points which do not satisfy the constraint. The constraint now is the graph of the differential inclusion, right-hand side of the differential inclusion, and h times y, because h is only in x, the pure state constraint. So you find the Lagrange multiplier. And it's very easy to get rid of L, to get rid of the epigraph of phi, as a matter of fact. It's subtransversal to the other thing, and obtain a transversality condition. But to separate, so you have something which is normal to the intersection of the graph and to h times y. Here you have two possibilities. Here you have to, maybe you want to write the normal as a sum of normals to one of the sets and normal, and that's the usual thing to be done. It's easy to be done if this difference is dense in x times y. This is the Clark tangent cone to G minus the Clark tangent cone to H times Y is dense. Then you obtain subtransversality as a null result as well of the sets and of the tangent cones, and you get normal intersection property. So you can express the Lagrange multiplier, which is non-trivial, in this way. In this way, the last thing is it's not a function, it's finite dimensional. It's finite dimensional, and thus one can, in fact, it is recovering the Euler inclusion, the Euler inclusion and the, and this is the generic. The Euler inclusion and transversality condition in the triangle maximum principle. What happens if this is not dense? Okay, then of course you can separate cones. I say of course, but I'm not sure that everybody are convinced in it. I don't speak about interiors or so on, just closed convex cone to be separated from zero, and it can be done. Then you have again something which is called Euler inclusion, but it is not very informative. So people say that when the last z, the real number is 0, and this sum is 0, this situation occurs, this, we checked it many times. This is the so-called degenerate case, the degenerate case of the Euler conclusion. Okay, and a lot of literature is devoted to when this degenerate case occurs. And we don't know why, but what's written here is a complete answer to this question. And it is in fact pointwise. It is in fact pointwise. So, having said this, if we restrict ourselves to the pointwise constraint where the interior of the Clark tangent cone is non-empty, then you can separate the cones exactly when the interior of this and the cone at the first coordinate for this is non-empty. Exactly then, if and only if. And in fact, it is a pointwise condition. It is a pointwise condition. This cone can be written as selections of pointwise selection and the other one. So you have some directions which go inside the constraint, which are tangent to the graph, if and only. So what's missing? Till this point I was boasting. And what's missing is something to be done, is missing the Warshaw's condition. We have to think more about it. And constraints on the velocities. We really hope to be able to use somehow the small ball in the second variable, but it's in the future. Who knows? And another, just an example, because the Pendragon maximum principle I spoke about is well established, and this is something which goes outside this series of paper, maybe 10 from 04 till the last year. Sergei Sept studied slightly evolving during the time problems of this type. He called them soft constraints and explained that maybe you have some contagious zone where you are not it's not preferable to go through it, but you can do it, but at some cost. So it depends on the cost. It depends on the cost. So you have not plus infinity. But in the very beginning, he has this lambda, just a positive constant, and that's it. That's it. And here it is again positive valued. But smooth. And he proved the Pendragon maximum principle for a problem of this type using the approach of Clark. L is Lipschitz, F is Lipschitz again. I'm sorry, here in Assel's paper, the differential inclusion was autonomous, that is, the first is superfluous. So, you have here it's preferable to stay in the complement, where self assumes this thing that is the tangent cone to the complement have no empty interior. And then, okay, what we can say that it is really straightforward to check that variational condition for dysfunctional, of course, subject to the mixed constraint, which is related to the differential inclusion. This epigraph satisfies the variational condition. And it is based on the fact that the epigraph of the functional is massive, n infinity times r. Of course, the graph is in the space times the real line. Let me say that we can, of course, recover just with no effort at all the order inclusion and the respective condition. They follow from our approach. And let me say that, for example, smoothness of lambda is superfluous. You can just say it is Lipschitz, no problems. And moreover, you can write a lot of integrands. Let me go back a bit. A lot of integrands here, which are not of this type, but still the respective functional satisfies the variational condition. For example, the example of a SF was you have the unit circle and you have, for example, the constant 1 over 8. Okay, put the hemisphere. It's not of this type. It's not Lipschitz around the boundary. Anyway, it satisfies the variational condition. So you have here a class of functions, of integrants, for example, which can be attacked using approach. Okay, thank you very much.
Any questions or remarks? Please.
I'm afraid I haven't understood much of the general theory, but about the optimal control problem you consider, you have state constraint, right?
Mm-hmm.
Pure state constraint, but you somehow avoid using measures.
No, it's just massiveness, that's it.
This massiveness,
It's big constraint, it's fat.
So
the interior of the clad tension.
So this massiveness actually is fulfilled if you have a finite number of integral constraints, for example, yes?
Yes.
So it's a kind of weakening of the finite codimensionality, sort of.
Okay.
Because if you have finite
It's just an example.
It's just an example. Finite codimensionality is with the strictly differentiable.
It's a weakening.
Okay, but this one, the other one, you have cones, finite Okay, you may say it. Okay.
No, it is the same as using measure. It's the same result because this function.
This massiveness is an assumption.
Massiveness is an assumption for applications. It's easy when you have pure state constraint. You assume massiveness on the first coordinate, and then the dynamics of couples of variation, the integral, and so they go outside. And massiveness is something which this approach. So Mikhail will speak about another, the same line, but with very thin constraints, okay? But then you need more smoothness. And this is very non-smooth.
Sorry,
Okay.
okay. People will hate me because of my question.
Sorry. We can speak.
I want to mention that, for example, the usual maximum principle considered by Winter, the assumptions are the same, but they assume openness of the quadratic pointwise. It's the same series. You see, it is very check too easy, and it is standard assumption in optimal control when you consider pure state constraint. So it's not artificial, so it's a very natural assumption. And it is very easy to check in concrete cases.
Okay. It's 15 minutes to 1 and
Okay, let's call the session. Thank you very much.
Check.